up and go down to Walmart. That's 50 pounds of bleach.
You're going to ingest 50 pounds of bleach?
Yep.
So, that's the first sentence that the camera picks up there.
And restart. Okay. Never floats your boat.
That's what we're doing tomorrow, so I don't.
I'm going to have to contact Mom and Pop.
Nah, you're good. Walmart. You kidding me? I'm going to Walmart.
I bought some one time.
So-
I know what I need to.
Alright guys. Yesterday we introduced a principle, the Chatelier's principle. I know those of you who weren't here, I maybe took more time going over it than I maybe needed to, just trying to, kind of give you the why behind everything. We talked about kinetics again and applied that to equilibrium. It's one thing to just know, oh, when you remove, you shift toward, and when you add, you shift away. Anybody can memorize that and not have a real good understanding of what's actually happening from a chemistry standpoint. So we spent a little bit of time talking about the why behind that. What was Le Chatelier's principle? What did he state?
You add or remove the reactant for the product, the other side.
That's one thing you can do to cause a shift. But what does the principle say that? Yeah. What does the principle say will happen? Because that's just one type of effect.
If a change is imposed on the system, then shift inside the reduce.
Yeah.
Hopefully having different K at different temperatures.
That's a true statement. I don't know how that has to do.
I'm sorry. That K would pertain to this thing. A change on the equilibrium, change temperature would be a different K.
We'll talk about that today. So what the whole idea with Le Chatelier's principle was that when a stress is added to a chemical reaction, just like when a stress is added to your guys' lives, you try to do whatever you can to remove that stress. It's the same thing for a chemical reaction. So if I add a reactant, it wants to remove the stress of that reactant being added, and the only way it can do that would be to react it and shift away. Okay? Or if I remove a product, that's the stress that I put on it. The only way to undo that stress would be to produce more product or shift toward. Okay? And we're going to take this idea and also apply it to pressure volume situations along with temperature situations. So, we're going to kind of talk about the pressure volume kind of together because we know that there's a relationship between pressure and volume due to Boyle's law. So if we increase the volume, we would decrease the pressure, and if we increase the pressure, we would decrease the volume. So we can really talk about that effect just by looking at volume. However, there are three ways where we can change the pressure of a gas. Okay, first one makes sense. If you add or remove a gaseous reactant or product, that's going to change the pressure. Move it, you decrease the pressure. You add it, you increase the pressure. Does anybody remember what inert gas is?
Yeah.
What?
An intermediate.
Good guess.
Just a, what's the term? Beginning and end of a reaction.
Always said intermediate. Is that what you're?
No. Those are used up state function.
Oh,
It's things that aren't really part of the reaction, but they include sometimes for no reason.
catalyst.
Like spectator ions, that kind of stuff.
Okay. Not quite. Well, kind of. Yeah, the idea. Yeah, absolutely that idea.
Okay.
So what an inert gas is, an example of an inert gas are any noble gases.
Yeah.
The reason why is because inert just means doesn't do anything in this context. So you could add a noble gas and it's not going to do anything because it doesn't react.
It'll keep away other gases before we react.
Well, it depends. You can use inert gases for a lot of, to try to prevent some stuff. Like if you didn't want, you wanted a gas, you wanted pressure, but you didn't want a chemical reaction to occur, you would use an inert gas. The thing with this here though, is that if you add an inert gas, Will it change the pressure?
No.
It will change the total pressure. It won't affect the partial pressures of the gases that you're dealing with. And so really it won't have an effect on the overall equilibrium because it doesn't affect your partial pressures of your reactants at all. Because if you remember Dalton's Law, that all gases exert a pressure independent of other gases. Okay? The fact that if I add one gas, it exerts the same pressure as if you put another gas in there under the same conditions. It doesn't affect the pressure of that original gas. Okay? And the last thing I just talked about with Boyle's Law, a way to change a pressure would also be to increase or decrease the volume. So, with all this being said, what does this look like from a Le Chatelier shift of equilibrium idea? Okay. It says when the volume of a container holding a gas is reduced, the system will respond by reducing its own volume. Why? This is a
Reduce the pressure to take off the
what's the stress?
high pressure.
What's the stress here? What happened to the system? The volume got reduced. That's the stress. So how would you undo that stress? You would reduce your own volume. Right? Because wouldn't reducing the volume create pressure? The way to undo that stress would be reduce your own volume to reduce that pressure. Does that make sense? Okay, so everything from Le Chatelier's principle is going to be based upon the idea that a stress is added and we want to remove that stress. So we could say this the opposite way. If you increase the volume, your reactor is going to shift to increase its own volume to try to undo the stress that was added to the system to get to equilibrium. Right? So here we go. So when your volume decreases, you're going to shift to the side with the smaller number of gas particles, and I'll explain why. Actually, I'll just give an example now. We've been using this a lot, we might as well just continue using this one. And these are all gases, does that make sense? Okay? So, let's see. Let's decrease the volume of this particular reaction. Alright? So if I'm decreasing the volume, the reaction wants to remove that stress by doing what? Decreasing its own volume. The question is, how does a reaction decrease its own volume? And what are you going to look at to figure that out? Yeah. So what you're going to look at here, how many gas particles do I have in the reactant side? And then pretty obviously we've got 2. So, does this make sense? If I produce more reactants, I'm going to be increasing my volume. And if I produce more products, I'm going to be decreasing my volume. More gas, more volume. Less gas, less volume. Okay? So if I cause a stress on here that decreases my volume, I want to shift to it's going to shift to decrease its own volume. Well, which way, based on this chemical equation, would it have to shift to make its own volume smaller? Right. Okay? So when you cause a stress, it wants to undo that stress. Now, if we were to increase the volume, that's the stress. I'm increasing the volume. It wants to shift to increase its own volume to negate that stress. Which way would it shift to increase its own volume? Does that make sense, everybody?
And if they're the same, they don't shift.
Yeah. Yep, absolutely. So like, if there was no coefficient here and it was 2 and 2, you could change the volume all you wanted, and it wouldn't change the equilibrium constant or equilibrium position. The reason why is because there's nothing the chemical reaction can do to remove that stress. Right? It can shift right or shift left, and it's going to stay the same. So, why don't you guys just apply that idea to this. Again, I know there's a lot of information up there, and probably not all that information that you actually need to read, but
Yeah, there's only one gas in the equation. There's no gas on the right. So does it have to have a gas there? And then goes to that?
No, it shifts right still.
Shifts right.
And then none, right? Because
You shift right, right, no shift.
the load would be none.
But it's like on a
Oh, yeah, I don't know why I put none. So it's right, none. Yeah. I don't know what that was.
and a bunch of leftover suckers from the Valentine's basket. So you guys want some?
I do.
Sure?
Yeah.
Someone could take two.
Oh, wow.
No, I wanted to.
No, Ben, you
I didn't get one
You can
yesterday.
take these two then.
Hey, are you going, wait,
Ben, you got through.
Ben,
Oh,
are you going to the Warriors game on Friday?
no, Saturday.
I'm going Saturday.
Did you get done?
Wait, what?
No!
We thought that too because he couldn't get to the second game.
Shut up. Alright, what did you guys get? Oh.
Right.
I was just.
Right, no shift?
Yeah.
Okay, so you were like, oh no, did I do something wrong? Shouldn't there be a left in there somewhere?
No.
Is that kind of how that all works? Can't do that. Right, no shift. Good. Temperature effect. Now, so yesterday we talked about concentration effect. This morning, at the beginning, we talked about the kind of pressure volume. They kind of go both hand in hand. And now we're going to talk about the temperature effect. The only one that can affect the equilibrium constant is this one. What I mean by that is when we add reactants or we add products or remove either of them, it will shift in a way and maintain the same ratio, so your K will always be the same. Right? When we did the concentration, anything we do to change the concentration, it will just shift in a way that maintains the same ratio, so your K value will always be the same. Same thing for the pressure idea. But temperature is different because you're not affecting concentration and you're not affecting pressure, which are the two things that we need for our equilibrium constants. So what you're doing is you're creating either more reactants or more products to ship without adding anything. And so the ratio is different. So what does that lead to? If the ratio is different, you're going to see a different what? Different K value. So, up to this point, we've been saying an infinite amount of positions, but only one equilibrium constant. Okay? But that was at a specific temperature. Does that make sense? Okay? So if we change the temperatures, we're going to get a different equilibrium constant. So here's how the temperature effect works. It's actually pretty more difficult than it maybe appears, and it's more difficult than I'm going to explain it. I'm going to kind of just give you the shorthand way of figuring this out. what we're going to do is we're going to treat anything that's exothermic, we're going to treat it as a as a reactant. We're going to treat energy as a reactant. And anytime we have exothermic, we're going to treat it as a product. So, did I?
Yeah, endo.
Oh, I meant to say endo at the beginning.
Yeah, it's fine.
Endothermic, we're going to treat as a reactant, exo as a product. So just, I'm going to give you a generic example. A plus B equals C plus heat. Which is that? Exo, okay. And I'll just reverse it, just make it easy. What'd you say?
Endo. So the reverse reaction is always the opposite, endo or exo of the fourth reaction, which makes sense.
All right, like if you have an exothermic reaction, the reaction is really stable and favorable for the products. If you reverse it, you're just going back to unstable situation. So it would be
Useful sometimes.
yeah, sure. All right. So I just want you to quickly know that what we're going to do to simplify this, and so we don't have, when we've got all these different types of ways to shift equilibrium, we can kind of keep it on the same idea. What we're going to do here is we're going to treat exo as a product, endo as a reactant, and then we're going to treat adding energy or removing energy like I'm adding a reactant or I'm adding a product. And then treat like the concentration concept. Does that make sense? So what I mean by that is if I add energy to this particular guy, the stress would be adding a reactant. Well, what do we do when we add a reactant? Shift right, in this case. Right? If it's exothermic and I add energy, it will shift left. And the same idea then will apply when you are removing it. Right? So, what else? Anything else I need? Okay, I already talked about K changes with temperature. All right. Do you guys remember how to use this information to tell you if it's exo or endo? Yeah. Which is which? Okay. Just want to make sure, So this guy's going to be endo. This is going to be exo. And so treat it accordingly and see if you guys can answer these questions.
Did that feel like listening a little bit?
I mean, yeah, I don't know.
You got it for?
Yeah.
Yeah.
Kind of a waste of $20, but.
Yeah, she said all she wanted was me to think about her. And then I got nothing.
Saying to play the times is good.
You did?
I've seen
Today?
that.
We saying to Terrence that.
Yeah. Yeah, he's so cute.
So like,
There's a kid
the
today
guys
that
will
was like,
have
that he's like,
10
"Oh,
more.
Mom, can I want one?" 'Cause I think
During
he saw
lunch.
them with yesterday.
No.
He's so cute.
So you don't say
So
all.
Titus was there. Titus was at home
So it was
yesterday.
like Tanner again.
Oh.
Yeah,
He's been
Titus.
sick for 3 days.
Yeah, Titus was there. We asked him, what do we think about it? He said, not really. No, I don't. No,
What do you think about it, Titus? Yeah, so, we were watching some home videos the other day of just, I don't know, kids are fun. What did you guys get?
Shift to the right, and
Right and left.
JK.
Now, can you predict this? How will the K values of each of these change? Can you do that? Why don't you write that down? Because we know the K values are going to change in these. How will they change? Will they go up? Will they go down? Can you predict that? Should be able to. We think about which way you're shifting, and what would have to happen to K if you shift it that way.
Same rate. So only two options.
Either increase or decrease K.
Yeah.
Or, I mean,
It's either the same or the opposite of the answer we just did.
you mean the answer.
The thing we just did. No. It should be the same, shift left or right, or up or down, or the opposite. I don't know.
You know which one? You don't think you can?
I probably could.
Okay, so you just wait for me to tell you.
Yeah. It's been.
If it's shifted right, what are you producing?
More products.
Products. In an
So it
equilibrium
decrease,
expression, you
so
have
it
products
decrease.
over reactants.
Increase.
So if you shift right, your K will what? Go up.
Yeah, that makes sense. I'm a little brain dead.
Whoa, you guys are
I've sung
brain
the
dead.
same 3 songs
wrote it
last
down.
3 days.
I know, I totally understand. Like, you just,
I'm brain dead.
I know, I feel bad for you guys, or for those of you who are.
We broke 100.
You what?
It's the first time we've ever broken 100 for some for guys who broke that together. We're not close.
That's the worst part.
Really?
It's like the singing,
Well, they're all-
like for the minutes, we have to go like West Des Moines to Aiken.
I feel like that would be like the fun part of it. You get to like chill out with.
You get to eat.
Yeah, lunch.
Yeah, we went to Pepper Jacks. They went to Smoky Row.
Oh, yeah, we went to